How do we find the distance between a point and a line when they exist in 3 dimensions? If you're wondering how to do this in 2 dimensions, go back and watch the previous video in this playlist. In 3 dimensions, we have a slightly different formula that we have to use. And first what I'd like to do is demonstrate how this formula works. So let's say that we have a line, and you can see the line here. And let's say we have this point, I'll call this point Q. And we want to find this distance. It's the distance between the point and the line, but it's the shortest distance between the point and the line, meaning this orange line that I have here is going to be perpendicular to my red line. Well, let's first pick a random point on the line. Let's say this point here. And let's imagine a vector traveling from that point to the point Q. And now let's imagine another vector. Let's say this vector here. With these 2 vectors, you could take the cross product, and if you take the cross product, you get this vector over here, right? A vector that's perpendicular to each of those vectors. And if you remember, the cross product has a very interesting property. It says the magnitude of that vector, of that resulting vector, will be equal to the area of a parallelogram formed by the original 2 vectors. So if those original 2 vectors I copy like this, you see this parallelogram we have, the area of this parallelogram will equal the magnitude of the vector you get when you do the cross product. Why is this important? Well, look at the line we're trying to find the length of, right? This orange line here. That's the height of your parallelogram. The area of a parallelogram is equal to its length times its height. So if you know this length here, and you know the area of the parallelogram, you can divide them to find this distance, this orange length. That is the basis for this equation that we're about to look at. The distance between a point and a line in 3 dimensions is equal to the magnitude of, I'll call it PQ, crossed with vector V all over the magnitude of vector V, right? This vector here, the green vector, that's your vector V. We're dividing the area of the parallelogram, which is this top part. We're dividing that area by that length of the bottom, that green vector. Okay, this is really like saying your height is equal to your area divided by your length, right? Because height times length is equal to area. You're solving for height, and you get this. That's what this formula says. This here, magnitude of your cross product, that's the area of the parallelogram. This here, that's the length of the bottom of your parallelogram, that green vector. That's how we can find this distance. Now, there's many ways that you can actually calculate the distance between a point and a line in 3 dimensions. This just happens to be my favorite method, and it's the one that I always like to use. And I also think it's a pretty cool concept. So let's do an example. Let's say we have point Q, and point Q is at 1, 1, 8. And let's say we have our line, and we have the vector equation of the line. The vector equation of the line is 1, 1, 2 plus t multiplied by 8, 6, 0. Well, the first thing we need to do is we need to find these 2 vectors, right? We have to find a vector that runs along the line, and we have to find a vector that goes between 2 points, the point we're interested in and a point on the line. Well, what is a point on the line? Well, you could use this point here, 1, 1, 2, if you'd like. But you could also use another point, right? You could plug in a random value for t and then figure out another point on the line. So just to make things a little bit interesting, let's do that. Why don't we say that t is equal to, I don't know, -1. And if t is equal to -1, you can find a point on this line, right? So if you do that, point on the line is equal to 1 minus 1 times 8 is -8. So 1 minus 8, which is -7. You could do 1 minus 6, which is -5. You could do 2 minus 0, which is 2. So you have the point -7, -5, 2. And in fact, that's the point we have plotted right here. Okay, so how do we make this vector here? Well, that vector goes from the point P to the point Q. So that vector, I'll call this vector V. In fact, I think I'll call it vector V1. Vector V1 is equal to, because it's going from P to Q, the Q values minus the P values. So 1 minus -7, which would give you 8. 1 minus negative 5, which would give you 6. 8 minus 2, which would also give you 6. So that purple vector that goes from point P to point Q, that is 8, 6, 6. Now we also need a direction vector. I'm going to call that vector 2. That's the green vector here that lies along the line, okay? Now you could just look at the vector equation and look at the direction vector in that equation and use that, 8, 6, 0. But in my drawing over here, I'm actually using a multiple of that. I'm actually using 16, 12, 0 instead. And the reason I'm using 16, 12, 0 instead of 8, 6, 0 is because I wanted to make this green vector a little bit longer just to make the picture look nicer and to make it easier to see where everything is. If that green vector is too short, then the picture just doesn't look as nice in my opinion. So I used a multiple of 2 and I'm using 16, 12, 0 rather than 8, 6, 0 for my direction vector. Again, it doesn't matter. You could just use this for this process, but I'm going to use 16, 12, 0 just to keep everything consistent with our diagram over here. Now, let me remind you of the equation, okay? The equation was the distance is equal to the magnitude of the vector that goes from point P to Q. So in other words, our vector 1 that we have written here. So vector 1 crossed with a direction vector that lies on the line. That's our vector 2. Right, that's this vector here. And then we divide it by that direction vector, v2. So this is the calculation we're going to have to do. We got to take that cross product, take the magnitude of it, and then divide by the magnitude of vector 2. So let's start off by doing our cross product. I'm going to come down here. The cross product of v1 and v2. And again, the order you do this won't matter. Like the order you do this will give you a different answer because it'll go in a different direction. But once you take the magnitude of it, at that point you will get the same answer. So don't worry about that. We'll do v1, v2. We set up our matrix. We have I, j, k. We have 8, 6, 6. And we have 16, 12, 0. We set up our answer like this. A little matrix times I plus a little matrix times j plus a little matrix times k. And sorry, this should actually be minus, not plus, right? We have a positive and then we do a negative and then we do a positive, okay? So first one, we cover this up. We have 6, 6, 12, 0. So that's what I'm going to write here, 6, 6, 12, 0. For j, we cross out j. What do we have? 8, 6, 16, 0. So 8, 6, 16, 0. For k, we cross out k. What do we have? 8, 6, 16, 12. 8, 6, 16, 12. Perfect. Let's do the calculations. For this first one, we have 6 times 0 is 0, minus 6 times 12. What's 6 times 12? 72. And it's negative because we're subtracting that. So negative 72i, okay? Over here, we have 8 times 0 is 0. 6 times 16, which is 96, so 0 minus 96. But then it's minus over here as well, so it actually becomes positive 96j. And then over here, we have 8 times 12, which is 96, minus 6 times 16, which is also 96. 96 minus 96 is 0, so we have plus 0k. So you absolutely can have a 0 value, and that's actually because my drawing, if I pull it up for a second here, you can actually see that there's no change in the height. Right? There's no change in our z value when you look at that cross product answer, and there's no change in the x value when you look at our line either. The line is completely horizontal. It is parallel to the xy plane. And the reason I did that for this example is just to keep the drawing a little bit more simple. You could absolutely have this scenario happen where the z direction or the z component is changing, and so this is more tilted up on an angle. It's just that for this example, I wanted to keep it simple. Okay, so let's get back to our cross product here. This means we have the vector negative 72, 96, and 0. Perfect. Now, we have to take the magnitude of this. How do we do that? Well, we take the square root of 72 squared plus 96 squared plus 0 squared. If you're wondering why I'm not including the negative here, it's because if you do negative 72 squared, you'll get a positive answer. So there's no point including that negative because this will be positive no matter what. And again, this is the magnitude of V1 crossed with V2. That's what we're doing here. So we do this calculation, and you should get 120 as the magnitude. Okay, perfect. Now let's look at our equation again. D is equal to the magnitude of the cross product, so 120, divided by the magnitude of vector v2. So what is vector v2 again? Well, vector v2 is 16, 12, 0, right? So we have to find the magnitude of the vector 16, 12, 0. So we write this out, 16, 12, 0. Okay, we plug it all in. We do this calculation, and if you do this, you should get 20. Okay, so over here, we have a value of 20. Perfect. So now the distance, all you have to do is divide here, and you should get a value of 6. So this is perfect. We have a distance of 6. So if you look at our diagram again, you'll see that this orange line here should have a distance of 6. And if you zoom in really closely and you look at this, I think that answer makes sense, right? So you have this point here, and this point is at a height of 8. We actually know that because the coordinates of this point are 1, 1, 8. And you have the line down here. And the line down here has a z value of 2, right? Everywhere, because the z value doesn't change. This is a flat line, right? And if you go back and look at the equation of this line, we actually have 1, 1, 2, right? And then plus t, 8, 6, 0. So the 0 means that the z value is never going to change. It is always going to be 2. So back to our diagram here, this line is at a height of 2, this point is at a height of 8, and that point is directly above the line, right? That point's directly above the line. So if you're looking at this orange line here, it would make sense that it has a distance or a dimension of 6, because down here you're at a height of 2, up here you're at a height of 8, and the xy directions aren't changing, right? So it makes perfect sense that this is 6. Again, this is a more simple example where you can look at it and judge that distance for yourself. But most of the time you do have to go through this process in order to calculate it. I'm just using this simple example so we can confirm our answer and so you can get the idea of how this all works. Okay, so you have your cross product vector over here. The length of that vector should equal the area of this parallelogram. The area of that parallelogram divided by the length, this green vector here, should give you this height, because the height times the base will equal the area. Okay, so it's a pretty nifty concept. It's a pretty cool way to do this, and this is, like I said, my personal favorite way of answering these questions.